Okay, welcome to chapter 15, where we're going to focus on water use, water management, basically all things water in relation to environmental science. The outline for this chapter is going to follow these topics. So first we're going to talk about the global water challenge. Then we're going to mention the water issue. Then we're going to talk about the hydrologic cycle, how we influence the hydrologic cycle, the different kinds of water use, kinds and sources of water pollution, and then we'll finish up with water use planning issues. Now, this is a fairly dense chapter. It's one of our longer chapters that we'll go over. And so, just kind of bear with me, pause the video, take breaks if you need to, because this chapter is about double the number of slides that we usually go through. So yeah, just kind of take your time going through this and make sure you kind of focus on everything, and again, take breaks if you need to. Okay, so the global water challenge. We have on the globe a specific amount of freshwater resources, and global population in terms of humans is growing, and so the demand of those water resources is rising. And as the populations grow, the demand comes in the form of water for drinking, sanitation purposes, water to produce food, water to make things, and then water for hygiene. Now, climate change is expected to kind of strengthen not strengthen, but contribute to let's see. So it's going to affect the need for this resource, right? So not the need, but I guess the availability. There we go. So climate change is going to affect the availability of water as a resource, because climate change is expected to make some areas much more drier, and that's going to contribute to the water stress in those areas. And so you combine the need of water for every person to live, the fact that population is growing, so that needs going to increase, and that climate change is going to lower the availability of water as a resource, is going to make it much more difficult to obtain water in the future for specific populations, especially. Policymakers therefore have to figure out how to supply water to the populations without degrading the water or the natural systems that provide the water. And as we know, water is very important. All living things are made up of water. We, our bodies are a majority of water, and water is what makes life possible. Water has amazing physical properties that we mentioned in the first chapter or so of this class. It has polar molecules that allow those molecules to interact with other molecules and cause those molecules to stick together to form hydrogen bonds. And they are also really good at dissolving other substances in a water solution. And it also stores heat and releases heat. So it's very important for regulating environment or climates. So things like temperature in surrounding areas. Not only is water important for living things, I guess the importance of water should not be focused on in terms of how much we have, or I should say it should not only be focused on the quantity, but we should also focus on how good of a quality we have in terms of the water source. If we have a lot of water and it's all polluted and nasty, we essentially have no water. So quality is just as important of quantity. And if we actually look at the amount of water that's available, right, we know that the earth is mainly covered, or a large portion of it is covered by water. 70% of the ocean is covered in the form of, or I should say 70% of the earth is covered in the form of oceans. and that represents 97% of the ocean's water. The remaining 3% of the water on Earth is fresh water, so the water that we can actually use. Now, even though we can use that 3%, there's an even tinier fraction that is only available for use. And so, of that 3%, we only have access and can use only a fraction of that. And the water that we can use is known as potable water. So, this is unpolluted, fresh water that we can drink and we can consume. Shortages of water can be attributed and directly correlated with human induced water pollution, as well as changes in environmental, in the climate, I guess you could say. And so the WHO has estimated that about 10% of the world's population does not have access to safe drinking water, which is a lot. That's millions of people, right, that doesn't have access to safe drinking water. According to the United Nations Environment Program, between 5 and 10 million deaths occur each year related to that are related, or these deaths come from water-related diseases. And there we go. So we're talking about things like dysentery, cholera, malaria, that all could be prevented if the people in these populations had access to safe sanitary water, potable water that they could consume. And these illnesses, unfortunately, have been increasing over the last decade because there's not been economic investments in the areas where these individuals live to provide safe drinking water. And so if that does not happen, if those investments are not made, then we'll just see the rate of deaths related to water-related diseases increase. Now, here's a figure showing freshwater resources. So here's your total water, and then 98% of that is oceans. And so we have just this little slice here that's fresh water. We pull that slice out. Of that fresh water, 78% of it is locked up in glaciers and ice. 21% is groundwater, 1% is in rivers and lakes, 5% is, or half a percent, is in soils. We don't even have access to the 21% that's in the groundwater, right? We can't access all of the groundwater aquifers. And so, we only have access to a very small fraction of the available water that is on Earth, and only a small fraction of it is potable or available for us to use. If we look at areas of the world that are experiencing water stress, we see the Middle East, East African countries, and North African countries are kind of the areas where a lot of water stress is present. So those are the areas where water is really needed. We need to provide that economic support. South Africa as well. You've got Spain. You've got Great Britain. And then you've got European countries that are water stressed as well. Now, looking at water and kind of how it is available or is available on the Earth is based off of the hydrologic cycle. So water's basically in this recycling process. So just like we look at nitrogen cycles, carbon cycles, that recycling process for those elements, we're also going to look at water and its cycle that happens on the globe, and that's the hydrologic cycle. So basically, you have solar energy that comes from the sun, and it will evaporate water. That water will then turn into a gas and rise into the atmosphere. Plants also give off water through a process called evapotranspiration. This is where water will leave their leaves, will exit their leaves as a gas and move up into the atmosphere. And so as that warm, moist water vapor rises, as it goes up into the atmosphere, it cools down. and as it cools down, it condenses and then falls back to the earth as precipitation. Now, some of that precipitation will remain on the surface. Some of it will infiltrate and percolate into the soil. Some of it will run off into rivers, lakes, and streams and oceans. And some of it will evaporate back into the atmosphere. Some of it will go from the soil into plants and then undergo evapotranspiration back into the atmosphere. Okay, and so that's kind of a summary of the hydrologic cycle itself. Now, runoff is basically where you have surface water that moves across the surface of the land and enters streams, rivers, or the ocean. Groundwater actually infiltrates underneath the soil and fills the spaces between the soil particles, so the spaces in that substrate. And then water that's in the soil is either taken up by the plant roots or actually keeps moving downward, keeps percolating downward to where it reaches an impervious layer of rock and then accumulates in the porous space there and makes what's known as an aquifer. Now, here's an example of water moving the hydrologic cycle. So you have evaporation, that cooling, precipitation, so that rain comes down, it will infiltrate into the soil or it will run off, go into the river, the ocean, or lakes. While it's in the soil, it will go down into the groundwater. It will be taken up by trees, by vegetation, in which it will undergo evapotranspiration. Or if it's on the surface, it will evaporate back into the atmosphere. And then that leads again back to condensation, where precipitation happens, and then the cycle continues. As I mentioned, the water can percolate down underneath the soil layer, and it can reach an impervious layer of rock, right? So like, imagine this is an impervious layer of rock that the water can't go down any farther. So the water will accumulate above this and will basically fill in that porous space. And that is what creates an aquifer. I have a better image to show you an aquifer here in a few slides. But we can have two different types of aquifers. We can have what's known as an unconfined aquifer that's usually near the land surface, right? So the surface of the soil. And an aquifer in general is just a layer of gravel, sand, or rock that allows water to move through it, that holds water, and then we can dig a well and extract that water. In an unconfined aquifer that's near the land surface, that top layer is usually saturated with water, and that's the water table. Then there's a lower boundary of an impermeable layer that's either clay or rock that holds that water kind of above that layer. Then the area above the water table is unsaturated, and that's known as the vadose zone, or the zone of aeration. Okay? The waters in these aquifers are at atmospheric pressure. They're not under high pressure, and so they're recharged by rainfall and then water percolating down through the soil layer back into the aquifer. Now, a confined aquifer is an aquifer that's underground and has a top layer that's impermeable to water and a bottom layer that's impermeable to water. So basically, the top and the bottom layer keep that aquifer in place. Water can't move above or below it. It has a specific recharge area that water will go into that layer from. Because these aquifers are bounded by those impermeable layers, they're under high pressure, and there's recharge from a geologic recharge zone, and we'll show exactly what that could look like here in a second. Now, the impervious confining layer is called an aquiclude. Now, if there's a permeable confining layer, that's called an aquitard. and we can measure the size and number of spaces in an aquifer in the substrate by its porosity, right? So if it has a high porosity, then it has a lot of space for water to sit inside that substrate. So here we have some examples of unconfined and confined aquifers. So here's your unconfined, right? So there's a layer on the bottom that holds that water. This area is the water table, and then above it, it's not saturated, so that's the vadose zone, right? And you can dig a well and you can pump that water out of that well. Now, this lower one is a confined aquifer. You have an impervious layer, another impervious layer, and the recharge area is up here. So water will enter this aquifer and flow down into this confined area. And this is an area that is under high pressure. And so you could have what's known as a flowing artesian well, which is basically water flowing out of that well because of the high pressure that exists from that confined aquifer. Now, a semi-confined aquifer would be one that is separated by an aquiclude, so that impervious surface, and then an aquitard, which is that permeable surface to water. So it's not completely confined. It has one impervious layer, but it also has a permeable layer above it. Okay, so next we're going to look at how humans can influence the hydrologic cycle. Okay, so runoff and infiltration are the two processes that are generally really influenced by human activity. You think of the amount of impervious surface that we put on the landscape in the form of roads, highways, buildings, concrete, parking lots, parking decks. All of that surface area cannot allow water to infiltrate into the soil. And therefore, all of that rain runs off of those impervious surfaces. And so one of the big concerns then is, where does all of that rainwater go? And the city, the urban areas, have to have an efficient transportation of that storm water, a drain system that allows for that runoff to drain effectively. If not, it leads to floods in those cities. So water withdrawals are measurements of the amount of water taken from a source, right? So you can measure that. And then if you incorporate water into a product, or if you lose it through evaporation, evapotranspiration, it can't be used in the same geographic area where it's consumed, okay? And so this storm water then can be evaporated, it can go into the atmosphere, or it can be withdrawal and used for another location, right? And so that storm water again has to be transported somewhere, either through evaporation withdrawals and moving it somewhere, or through, say, a drainage system. And so looking at next the kind of water use that we do, so basically how we consume water. If we want to maintain our population, if we want to, help with this water problem, we really need to think about the conservation of our aquatic resources. And the quality and quantity of water is really important, not only in supporting us as human beings, but also in supporting ecosystem services. Because again, if you ruin these ecosystem services, you're also ruining the resources that they provide. And those ecosystem services are being jeopardized by population growth, urban migration, resource consumption, and climate change. And so not only is it ecosystem services, but also the water that's being affected. And so there's data that suggests that if these trends continue by 2025, so within 4 or so years, 1.8 billion people will have water scarcity, and 2/3 of the world's populations could experience and suffer from water stress. That's a big number, right? So that's a big issue. And so the different ways that we use water, we're going to kind of go over in the next couple of slides. So first is the domestic water use, so the domestic use of water. So over 90% of the water used for domestic purposes in North America comes from municipal water systems. On average, an individual in North America uses about 100 gallons of water per day. This is to wash clothes, wash lawn, toilets, bathing, etc. 29% is used to keep your lawn and garden up, and 2% is used for consumption, so drinking and cooking, right? So we use a lot of water for other aspects of our daily lives rather than consumption, right? So here's looking at the breakdown of that domestic water use for a family of 4 in North America, okay? And so with this water use, we're creating a lot of waste, and the natural processes can't deal with the wastewater that we contribute to the ecosystem. And so what that means is they naturally can't treat that water and make it potable again. So what we have to do is treat it before we release it back into natural systems. But the problem is that's really not done correctly and appropriately. So in 2011, there was a study that looked at chemicals found in the drinking water of 45 states, and they found all of these chemicals: industrial solvents, weed killers, refrigerants, rocket fuel components, percolate. And so there's just nasty stuff, unfortunately, in our water sources that just shouldn't be there. And, besides the pollution issue, there is a public attitude that we have that allows us to kind of contribute to the water loss and the overuse of water. A lot of people look at water as being this limitless resource. It's inexpensive. And so because of that outlook, there's not a lot of conservation methods that are taken to conserve water. However, if you look at the number of states reporting water stress, that's 46 out of 50. That's almost 100%. Especially if you're in the western states, you're really vulnerable to this water stress issue. Shortages of water are increasing, and purification costs are increasing, and so that's making the price of domestic water go up. If you have shortages, if you don't have enough supply, if it costs a lot of money to purify that water, then it's going to be expensive compared to what it was before, and it's going to be hard to get to areas that don't have water. And so the increased costs will lead to reduced use. So for example, China is setting quotas on water use that are enforced by higher prices for larger users. So if you use a lot of water, your price for that water is even higher. And then at the federal level, the EPA, for example, is currently developing a national consumer labeling program of water efficient products. And it's modeled after this energy efficient STAR program. And so looking at conserving water and a program that's kind of dedicated towards that. And so not only are we trying to get the public to conserve water, but the municipalities have to pay attention to the losses that happen within their distribution system. So for example, leaking pipes. Leaking pipes lead to a significant amount of water loss. Even if it's in a developed world, you could lose upwards to 20%. Poorer countries may lose half of their water due to water leaks in that leaky system. Okay, we're just going to kind of skip this one. Okay, maybe not. So this one here is just showing the percentage of water use based off of domestic, industrial, and agricultural. Right, so we're saying the world primarily uses ag, so like 70%, with about, what's that, 20% for industrial, 10% for domestic. Whereas if you're saying other parts of the country, those numbers, or other parts of the world, those numbers are going to fluctuate. Like North America uses a much larger proportion for industry than it does compared to most other countries except for Europe. Okay. And so we've already just finished discussing domestic water use. Now we're going to look at agricultural water use. In North America, groundwater, so pumping water out of the ground, is about 43% of the water that's used for ag. Surface water makes up the remaining 57%. And irrigation is one of the bigger kind of forms of water transportation that allows for water to get to these ag areas in most parts of the world. It accounts for about 80% of all water consumed for North America, so process of irrigation. Now, there are 4 common irrigation methods. So you have surface flood irrigation, spray irrigation, trickle irrigation, or sub-irrigation. Surface flood is basically where you flood a field and you irrigate it that way. Spray irrigation uses pumps to basically do a spray, almost like a water sprinkler. Trickle irrigation is almost like it's a drip irrigation where you place openings directly at the base of a plant so that the water drips directly onto the plant roots. So you're kind of placing the water more precisely than you are with spraying and flooding. Sub-irrigation uses underground pipes to supply water to plants and can also be used to drain a field as well. Costs for irrigation's typically been low since a lot of dams and canals were built using government assistance. However, there is competition for scarce water resources in some areas, prompting communities to raise water rates for irrigation, causing farmers to find ways to conserve or recycle water. And the high demand for irrigation can also be reduced by reducing the quantity of water demanding crops in dry areas. So the more water demanding crops you have, the more water you have to use. So this is an example of kind of the flood irrigation. And then this is probably an underground irrigation system, maybe so pipes running underneath this plastic, which helps to keep heat in and keep the soil warm. And so the pipes are probably running in there with water, going into the roots that way. Is what I would guess. I'm not 100% sure. But the big thing here is it's showing that it's irrigated with recycled water. All right, next is industrial use of water. So industrial use accounts for nearly 50% of all water withdrawal in the US, 75 in Canada, 23 worldwide. 90% of the industry water is for cooling as a return to the source. So we actually don't consume that water in when it's being used for this method. Mostly it just involves heat exchange. So taking the heat from the product that it's cooling or the machinery that it's cooling and allowing that water to take up that heat and then be recooled and then recycled in the system. But water is also used to dissipate and transport waste. And if those wastes are put directly into a stream or a lake, then it can result in the degradation of that system itself. So because of this, we have the Clean Water Act seeking to protect waters in the U.S. from these type of pollution sources. So it regulates the discharge into navigable waters by setting a water quality standard for surface water. So basically saying surface water can only have this amount of this substance, this amount of this substance or chemical found in that water. If it's more, then the company or facility or source has to be found, and then they are likely going to be held accountable, being fined, all of those things. And then you also help with this by limiting the discharge into the water. So the amount of effluent discharge that goes into the water itself. So if you have less of that, you have less chance of those pollutants making it into the water sources. Now, the final use of water is in-stream water use. So this is using the water, say like in streams and lakes and canals and in river basins, etc. And these are non-consumptive. So you're basically using them for recreation, for transportation, or for hydroelectric power, like we mentioned when we were talking about energy types, when we talked about hydropower producing electricity. Currently, hydroelectric power plants produce 6% of all electricity generated in the US, so that in-stream water use is a big deal when it comes to the energy sector. Now, even though those hydroelectric dams are creating electricity, they control flooding, but they do have some drawbacks. There are some cons in having hydroelectric dams. The first is that they cost a lot of money. The second is that they destroy habitat. So they flood the areas behind it, and then they can cause flow changes in the areas below it, and they also can keep migrating fish from reaching their spawning grounds above the dam. The dams reduce the effects of flooding. So even though they're controlling flooding, they also reduce the flooding downstream. And so now the ecosystem that was usually flooded every year, let's say seasonally, is all of a sudden not flooded seasonally because that stream flow is reduced and changed. And so not only is the stream flow changed, but also the silt deposition downstream is changed as well, because you'll get that silt and that sediment to be blocked behind the dam and never actually make it downstream, which changes the ecosystem downstream. And then the impounded water has an increased evaporation rate because it's now in a reservoir and it's not this moving river anymore. And so the rate of evaporation changes whenever you have a dam constructed. And a lot of urban areas will rely on water to transport resources. So for example, the inland water system in the US carried 10% of goods like grain, coal, or an oil. And so we're talking about, billions of dollars worth of material that's being transported through these water systems and waterways. So even though it's non-consumptive, still using quite a bit of it for goods and resources. So here we have dams that are interrupting the flow of water. So we have kind of a regime change in the stream system due to a dam. And what we're kind of going to get into next is what happens whenever you have water pollution and what the types of pollution can lead to into streams and rivers and lakes. And so let's say, for example, we have this factory, and this factory is releasing water into wastewater into the river. This wastewater could have a lot of dissolved organic matter in that water. And so basically you have a lot of organics here that need to be degraded. So you have a high biochemical oxygen demand because you need a lot of oxygen to break down and decompose the high amount of organic matter in this area. So because you need a lot of oxygen to do decomposition, and there's so much organic matter, decomposition is basically occurring all the time, the available oxygen in this area will be used up. See how it says 0 parts per million in terms of oxygen concentration in the water, or dissolved oxygen, that means there's no oxygen here, so no organisms can live. As you get farther downstream away from that source and the organic matter starts to become less and less, you get your dissolved oxygen concentration to begin going back up. But this recovery zone, as it says, is several kilometers downstream. This image is not to scale, right? So this is a very long distance that it takes for the stream to recover and to get back to high enough oxygen, dissolved oxygen concentration levels to where it's a healthy stream again. And another factor for this is that once all of the oxygen is used up, the anaerobic bacteria will then start to break down waste. This is bacteria that breaks down organic matter without the presence of oxygen, and that produces this kind of foul odor, almost like a rotten egg sulfur-based smell. And so if you've ever been around a wetland or a place that has a lot of organic matter kind of on the floor of the oxygen or water layer, then it will lead to low oxygen, dissolved oxygen, because all of that organic matter is going to be broken down. And so this is the BOD we were talking about, the biochemical oxygen demand. So it's basically the amount of oxygen required to decay a certain amount of organic matter. The more organic matter you have, the more oxygen you need in order for that to happen. And so the bacteria will use up all of that oxygen, and you could get what's known as a dead zone. And so a dead zone is basically where aquatic organisms can't live because there's a lack of oxygen. Next, you can also have disease-causing organisms as a pollution problem. So if you have untreated or inadequately treated human or domesticated animal waste, they can lead to organisms and pathogens that could cause problems if you drink that water. So things like Giardia, E. coli, etc., can enter those water systems and cause big problems for diseases in that pollution. Now, nutrients can also be a pollution problem. You might not think about it, but nutrient runoff from an ag system, so like more nitrogen or more phosphorus, could actually be a pollution issue, because what that is a lot of the time, say, nitrogen is a limiting factor in aquatic systems. If all of a sudden you have an impulse of nitrogen into that aquatic system, the algae and the plants are just going to explode in terms of growth because they have all of these nutrients. You're fertilizing the water basically. And so you get what's known as eutrophication to happen. And that excessive growth can cause the water clarity to go down. It could cover spawning sites of certain species. They can be abrasives. They can become thick and injure organisms. Those algae, those phytoplankton can also carry toxic materials, but it also adds to the organic matter. And if you get enough organic matter to grow and fall to the bottom, all of a sudden you have a high BOD issue now. So that decomposition is going to happen, and you can end up with a dead zone because of eutrophication from water runoff. And this is actually a problem in the Mississippi Delta because the Mississippi drains, the interior region of North America basically, and all of the runoff from those ag farms in the interior region of North America goes into the Mississippi. Then all of those nutrients go out into the Mississippi Delta in the Gulf of Mexico, and you have an explosion of phytoplankton. They die, fall to the bottom, become broken down by the bacteria through decomposition. They use all the oxygen up. You get a dead zone that exists. And so then aquatic organisms can't live in that area. Other kinds of pollution sources are, say, point source pollution. So point source pollution is where you actually have like a pipe that is discharging waste into the water, the river, the stream. Non-point sources are much more difficult to identify because these are things like acid rain or pollutants from agricultural land or runoff of paved services that don't come from a pipe source, that aren't directly discharging into a water or aquatic area out of an obvious pipe or obvious transportation system. Now we can protect surface and groundwaters from non-point pollution through a variety of different methods. Using less toxic or non-toxic alternatives for our home chemicals. Buy chemicals only in the amount we intend to use. Apply conservative amount. More is not always better because that excess will run off and go into our water system. Take household chemicals that are hazardous to waste collection centers. Don't pour them down the drain. Don't pour them out in your yard because they will go into our water system. They don't just disappear into the soil to never be seen again. They'll dissolve into the rainwater and then percolate down into your aquifer, and you may drink it in 10 years. It can happen. So you want to, especially if you have a well that you get, water out from under your yard. So you want to make sure you're paying attention to these things and you're not pouring those unwanted chemicals on the ground. Use water-based products whenever possible. When landscaping your yard, choose native plants that require low amounts of water, fertilizers, and pesticides. And then test your soil before applying fertilizers and look into natural ways to increase other nutrients. So say like if your soil is low in nitrogen, then maybe plant some legumes that will fix nitrogen into the soil, and then plant plants that can then take advantage of that. And so try to think of natural ways to help with the issues that you're having with your soil and maybe growing your plants. Other ways that water pollution can happen is through municipal water pollution. So for example, waste from homes that are primarily organic matter. So thinking about garbage, food material, wastewater, gray water from cleaning clothes or dishes or human waste can also be sources of water pollution. So for example, fecal coliform bacteria is bacteria that's generally found in the intestines of warm-blooded animals, so it's associated with wastewater. So that's things like E. coli or strep bacteria. And if the numbers and types of bacteria present in the water are directly related to the amount of fecal matter entering the system. So if you have a lot of fecal matter entering a water source, then you would expect to see high amounts of E. coli and high amounts of strep. If you don't have a lot of that pollution, then you wouldn't expect to see any of that fecal coliform bacteria. And so, for example, in January 2011, you had over 2,000 Haitians die from a cholera outbreak due to contaminated drinking water. And again, these are deaths that could have been prevented if they had better access to more efficient sanitation practices, as well as cleaner drinking water accessibility. Wastewater from cleaning dishes and clothes and washing, so like with soaps or detergent, is a big water contaminant. So many detergents contain phosphates, which contributed to eutrophication. But these phosphates were eliminated from a lot of major detergents since 1994, so that issue of phosphates has begun to go down. Also, drugs and medicines being washed down the sink or flushed down the toilet, so like your pharmaceuticals, different hormones, so like birth control, etc., insecticides, all are found in municipal water discharge and can pollute certain aquatic sources. So for example, in 139 streams examined in the US, The USGS found one or more chemicals in 80% of the sampled streams. And these chemicals largely don't get regulated and are not removed from municipal wastewater treatment. So we will drink them again, if that water is moved through the municipal system. Agricultural water pollution, again, comes from agricultural activities. So excessive fertilizer use leads to eutrophication. So that runoff is a big issue. We've talked a lot about this before, but ways that you can prevent this is from leaving a conservation buffer between your fields and the streams. Keep the soil covered with a crop. So whenever you harvest it, put a cover crop on until you go to plant it again, and then to control the amount and the timing of the fertilizer applied. So again, you're reducing how much goes in the runoff. Now for industrial water pollution, so you have factories and industries that frequently dispose of waste in the sewage systems. These wastes require special wastewater treatment facilities, and we'll talk about how wastewater is treated here in a little bit. And then mining is also an source of industrial water pollution, where chemical runoff goes into streams, and water drainage from mines is highly acidic, which can really affect the biology and the natural processes in those streams and aquatic sources. Another form of pollution is thermal pollution. So this is where you have an industry that's using water from a source for cooling purposes and then returns that hot water back to its original source. So for example, steam from steam turbines has to be condensed into water after leaving the turbine. So that increase in temperature could affect aquatic ecosystems. It could kill fish, it could kill plants or other organisms that are in the area where that warm or hot water discharge exists. And so especially, in the industrialized world, most cooling water is not released in the way that aquatic ecosystems are endangered, but it still happens in certain areas. Other methods of discharge heated water are, for example, shallow cooling ponds. They allow the heat to dissipate from the pond before they release it. Cooling towers, the heated water is sprayed into the air, cooled by evaporation. And then dry towers, heated water is pumped through tubes to release the heat to the air, kind of like a radiator does. And then that water can then be released into the system. There are also sources of marine oil pollution. We talked about this some in an earlier chapter. So the oil pollution can come from accidents, so like the Deepwater Horizon spill or oil tankers crashing or running aground and leaking. But a lot of the marine oil spills come from average just transportation uses. In terms of the oil that is spilled, 50% of that is 50% of the spilled oil biodegrades on beaches or in the water. 20% is evaporated, 14% is recovered, 12% is on the bottom of the sea, 3% in the shorelines, and 1% is still adrift. So this is generally kind of the ratios you would expect whenever you have an oil spill to happen. Now, tanker accidents are spectacular. They release a lot of oil at one time, and so you obviously know when that happens. But like I mentioned, a lot of the oil pollution comes from just everyday use, street runoff, improper disposal, intentional discharge during, I think they should say unintentional oil discharges during tanker loading and unloading. So like spills that happen as you're putting it into a tanker or taking it out of the tanker. So there was an agreement reached in 1992 that declared that oil tankers must be double-hulled, and only double-hulled tankers are allowed in the United States to try to help with that pollution source. Now, another source of pollution is groundwater pollution. This comes from runoff and infiltration into the soils, so through the soils into the water, so things like agricultural products like pesticides. Storage tanks underground can leak. Landfills can leak into the water system. So all of the stuff that we bury in our landfills do not have any kind of system to collect the leachate that comes from that, and so it seeps into the groundwater supply. Septic tanks can lead to leakage into the groundwater. So there are over 20 million septic tanks in the U.S. About a third of those don't work properly. So that means that sewage is leaking into the groundwater system. Surface impoundments are mostly not lined. And if they are, 1% use a plastic or non-soil liner. 99% can't tell if they have leaks, and 73 don't have a restriction on what wastes are put in the impoundment. So you have a lot of leakage that can happen into the groundwater, right? So you have leaking sewers, leaking septic tanks, leaking from businesses like gas stations, etc., landfill leakage, seepage through oil wells or waste wells, waste lagoon leakage, accidental spills. So all of these can infiltrate and move down into the groundwater system itself. Now, finishing up and looking, well, not finishing up, getting close to the end, but starting to look at water use planning issues, okay? So in the past, wastewater and waste were discharged into waterways and streams without any thought of kind of the cost that would be imposed on the users of that stream because of the decrease in water quality. And as population has grown, domestic water use is intensified, and so there's not enough water to meet everyone's needs. And so now we're also looking at the effects later on of how these waste discharge has affected the health of the human population, combined with water shortage and having a water source nearby that's polluted and you can't use it when you don't have water in general, brings this to everybody's attention. So basically, you now have metropolitan areas that have to deal with and provide three basic services. So you have to have a water supply for human and industrial needs. You need to have wastewater collection and treatment, and you have to have stormwater collection and management. And like we mentioned, because these urban areas are paved, very little infiltration, lots of runoff. And so the Water Quality Act of '87 basically says that municipalities have to have permits for discharge of stormwater runoff so that non-point pollution sources are controlled, right? So they're controlling the pollution that runs off with that stormwater runoff. So many cities have separated storm sewers from sanitary sewers so that the contamination in times of flooding and heavy stormwater runoff, so basically they don't mix with each other, right? So they're avoiding those contamination issues. Future issues have to be addressed though. So for example, increased demand will generate pressure to divert water to high use areas. So where there's demand, you're going to have pressure to put water there. If there's an increased demand for wastewater treatment and the reuse, so recycling of existing water, salt buildup due to evaporation, so basically salination can lower water quality. You could over pump groundwater, cause water tables to be lowered or aquifers to be used. Seawater intrusion, so sea level rise happening, causing seawater to percolate through the soil and run into coastal aquifers, can actually ruin a water supply and turn it salty and basically not be fresh and usable anymore. There's also going to be an increased demand for water-based recreation, And so you need good water quality for that to happen. Nobody wants to swim or ski in polluted water. So next, looking at water diversion. So water diversion is basically the act of moving water from one place to another, and is super necessary pretty much all around the world. However, when you divert water for irrigation, water bodies downstream are deprived of their source of water. So basically, stream levels, lake levels decline. It affects fish populations and other wildlife populations. So we have to be conscious of this whenever we irrigate and we move water around. Next, looking at water treatment and basically how we treat water. We go through these different stages of water treatment, kind of at these water treatment facilities that will remove certain pollutants depending on the stage of treatment you're at. So, primary sewage treatment basically removes large particles through a filtration process and then pumps the remaining water into settling ponds and lakes. This allows all of the stuff to settle out of the water. And then the water is pulled off of the top so that you don't pull the particulate matter that was on the bottom. And if it still has a large load of organic matter, or I should say, this settled water still has a lot of organic matter, dissolved salts, bacteria, and microorganisms, and needs to be treated even further. So then you can enter the secondary sewage treatment, where biological processes that will basically cause the bacterial organisms to degrade the organic matter. The wastewater will be mixed with oxygenated water so that that can happen, so that that decomposition can happen. And then it will be moved through what's known as a trickling filtering system, where the wastewater is sprayed over a rocky surface to increase the amount of dissolved oxygen that's present in that system. And then with the sewage sludge, which is the particulate matter that's settled out during the treatment process, a mixture of organisms is contained in that particular matter as well. So you have organisms, particulate matter, that is basically a byproduct of the treatment process. Activated sludge sewage treatment plants will hold wastewater in settling tanks with air that's continually pushed through, and the water and sludge will basically become separated from one another and then processed further down the line. So this is an example of primary and secondary treatment. So you have your settling ponds here on the left-hand side, and then you have that trickling over the rocky substrates on the right-hand side. After that secondary treatment, you have the tertiary sewage treatment. So this is an additional stage to remove inorganic nutrients like phosphorus and nitrogen that's left after the first two stages of treatment. This is very costly because you have to have certain chemicals to treat the water. One way that you can do this, though, is to use natural wetlands or constructed wetlands to help to filter these nutrients out of the system. Some areas will use effluent to basically irrigate golf courses or vegetation because they take the nutrients from that water and prevent it from being released into the straits, into the lakes and the streams. So pretty interesting ways to deal with those inorganic, or I should say those nutrients, not inorganic, the nutrient compounds. So the next issue we have with water is salinization. So this is basically an increase in salinity due to increasing salt concentrations in the soil. So basically, as plants remove water from the ground, the salt that is present in the water stays and becomes concentrated. And so irrigation of an arid farmland can cause that salination process to become basically to happen faster due to increased evaporation rates. And this is especially an issue if the areas have been irrigated for many, many years. And then you also can get this saltwater intrusion that we mentioned earlier. So basically, sea levels will rise and the salt water will infiltrate into the freshwater well. Or you could get overuse of that well, which brings up all this fresh water and allows the salt water to come in and infiltrate that well. And then you have to dig another well, and it would just keep infiltrating and intruding into that freshwater aquifer. Now, a way we obtain water is sometimes I guess I should say sometimes we over harvest water and we remove it from an aquifer faster than it can be replenished through groundwater recharge. And this is known as groundwater mining. And if you have vast periods of mining, you can basically have subsidence, which is where the land actually settles down and lowers because the air spaces that held water between the sand pores or the sediment pores don't hold anything now except for air. And so the weight of the land above it can cause it to settle and pack tighter, and it can basically go down several feet. You could also lower the water table, or you could cause that saltwater intrusion to happen like we just showed in the previous slide. On average, about 85 billion gallons of groundwater are taken out of the ground daily in the US. 90% of this water is for irrigation, public supplies to homes, businesses, and industry. 2/3 of that is for irrigation. Groundwater is about half of the drinking water in the US, and a lot of rural areas depend on groundwater for drinking. So, for example, wells. You'll put a well pretty much in everybody's yard, and that's where their water comes from in these rural areas. For example, where I grew up and where I live in North Carolina, our yards are so we have wells that we get our water from. We have to pay somebody to dig it, put a pump on it, and that's where our water comes from. A lot of the farms in Merced County had irrigation and also had well water to help supply some of that water to their crops and fields. The use of groundwater has increased, especially between 1950 and 1975, especially whenever you're looking at arid, semi-arid countries or states. So millions of independent farmers depend on that groundwater for generating crops to get their economic benefits. Little management by government water agencies in these places. And if you look at it in terms of globally, about 2 billion people depend on groundwater for a drinking resource. And so, that can show why there's a lot of groundwater mining that actually happens, because it's such a large, such a primary way that people get water as a resource. Ways that we can kind of manage this groundwater mining issue is to shift from groundwater to surface water, to import water outside from local areas, but then that leads to issues that you get with irrigation. You control pumping with guidelines, policies, you could tax it, you could regulate it, etc. There are different conservation practices that we could impose. We could reuse our gray water. So like water you use that you wash with or you wash dishes with, you could reuse it in some way. You could treat that wastewater, so reclaim it, basically use it for non-potable purposes, and maybe look at desalinization. So like brackish water, but desalinization is pretty costly and expensive technology currently. Some bodies of water may not be, say, used for drinking or for a potable resource, but they can be used for, say, scenic value. So, for example, the United States Federal Wild and Scenic Rivers Act established a system to protect wild and scenic rivers from development. The Merced River has a portion of that river that is a wild and scenic area. All federal agencies have to consider the wild, scenic, or recreational values for rivers whenever they look at how they are going to develop land that is adjacent to that river. So if it is a wild and scenic river, there are implications for the developmental process that they have to take into consideration in that area. For water use planning issues, historically poorly drained areas were considered worthless. They were filled or drained and then used as building sites. So what this means is that a lot of the wetland areas were drained or converted to different types of habitats or urban areas or ag areas. And this is what this figure is showing, is the causes of wetland loss. So basically wetland conversion is for a forestry resource, for agricultural land, you convert it to urban areas, or you have some sort of rural development. And so these are the primary causes of wetland loss from 1986 to 2010. Now, in the US, 95% of the remaining 20 million hectares, so 50 million acres of wetlands, are inland freshwater wetlands. And these are areas that are likely to be considered valuable to be converted into ag areas. Only recently, so recently being the last couple decades, has the economic importance of wetlands been recognized, and the kind of environmental service or ecosystem services that they provide really been understood and brought to the public attention, and the public actually kind of seeing that. Wetlands are really important for wildlife spawning and breeding habitats. We've talked about this one quite a bit. They also serve as natural water filtration systems. I've mentioned this in earlier chapters, but we also talked about this in this chapter itself. It also helps to slow floodwaters and allows nutrients and sediments to settle out. And then it also serves as floodwater control. So it serves as a basin for those flood waters to basically flow into and to not come up in the higher areas, say where your house or your city may be. And so again, the value is filtering the water, toxic waste, nutrients, preventing erosion, providing floodwater storage, providing resting spots for migratory birds. Big reason for wetlands in the Central Valley. The Central Valley is part of the Pacific Flyway. You know, millions of migratory birds fly through every winter. They stop over. You have sandhill cranes. You have all kinds of geese and duck and other waterfowl species that come through that use those wetlands as stopover spots. And if those wetlands go away, they don't have those stopover spots to gather their energy, and therefore those species could really be negatively impacted because of that. They also provide food and habitat for other aquatic species, so other aquatic animals, and then nursery sites for young. Again, I've talked about this super, a lot over the course of the term. So wetlands are really important in terms of ecosystem services, and we're now kind of starting to see that and realize that. And there was a Wetland Act that was passed, the Ramsar Act, I believe is what it's called, where it's valuing these bodies of wetlands and putting a kind of conservation effort into keeping them intact. And so here's the summary outline for this chapter. Like I said, this was a fairly dense chapter, so a lot of material to go through here. So make sure you use these summary slides, as always, as a key starting point for your studies. And as always, this is not all of the information that you need to focus on, but just a good starting point for when you do study. And let me know if you have any questions. If you have any concerns, you can contact me via email. You can contact me via the class discussion board. And with that, I hope you have a good day, and we will see you in the next chapter.